This is Professor Hill, and what are we going to do today? We are going to try to understand water and ocean structure. It gets a bit technical, so I'm breaking this down into, I think, 2 or 3 lectures so that we can, have breaks in between. All right, these outlines I put here, they're for your benefit so that when you're getting ready to study for exams, you could go through the outline and say, what do I know about this subject? Talk yourself through it and find out, do I understand this enough to take a test on it? All right, water is magical sort of element on our planet. It has properties that no other element has, and if it wasn't for water, we wouldn't have life on this planet, which is, of course, why we look for water on other planets when we're looking for life. This is one of those old-fashioned pictures of a depiction of a water molecule. You've got your big oxygen molecule and your 2 little hydrogens on the outside. First thing to remember is, I've told you this before, is it's a polar molecule, meaning it has positive and negative ends. The oxygen end is more positive, and the hydrogen ends are more negative. Because of this, it's attracted to other water molecules. That's what these little Mickey Mouse kind of looking things are. The red is supposed to be oxygen, and the grays are hydrogens. The positive ends are attracted to the negative ends, and it's a very loose attraction. It's called hydrogen bonding, but it's very loose. They can change, and they may be attracted to this molecule right now, but they'll be attracted to that molecule in a second, which is why, if you have a pitcher of water here, and I take it and I pour it into a different pitcher, it changes the shape to meet the new pitcher, no problem. It'll break its bonds with whatever molecule it might have been next to before and rearrange so that it fits in the new structure. And I told you before also that, it's because of this polar nature of water that rocks weather, because over geologic time, water raining down on this planet and moving across its surface attaches itself to positive and negative ions, which is what a positive or negative element is called. Is an ion or a cation, but we're going to just talk about ions. And it takes these and dissolves them out of the rock and takes them to the ocean, silts out, and causes erosion and weathering and deposition and sediments on the bottom of the ocean. Okay, so this attraction they have causes water to have a whole bunch of extra properties. So look at we noticed that water droplets tend to be round. Why are they round? Because they're attracted to each other. It's the most compact shape you can have when you're all attracted to each other, is a round shape. That causes a surface tension around the edges of the water, which is why water spiders can walk on the surface of water, because those positive and negatives that are attracted to each other are causing a surface tension. Also, they have glorious mud there. The positive and negative ends, as I've mentioned before, are attracted to positive and negative elements in sediments, which mud, of course, is a sediment. And if you've ever licked your fingers and then you used your wet fingers to either open a plastic bag or to turn the page of a book, that's because when you lick your fingers, you're putting water on them. And so you're making a weak glue that goes away when it dries up. And so for a second, your fingers stick to things. Thermal properties of water. All right, let's get a couple definitions out of the way here. Heat and temperature. Heat is basically the vibration, the energy of the vibration of molecules. Temperature is our measurement of heat. So this bathtub full of hot water probably has more heat than the candle, or one candle, maybe, I'm not sure. But the candle probably would have a much higher temperature, obviously, than the bathtub water. All right, a couple other definitions. These ones are kind of tricky because they're very similar. Specific heat. They should be in your book, by the way, so if you need to look them up. Is the amount of energy measured in calories calories is a measurement of energy, to raise the temperature of a unit mass, that means a certain amount of something, 1 degree Celsius. So here it looks like we're raising the temperature of clear liquid, maybe it's water, maybe a cup of it. And what's important for us is the specific heat of water. The specific heat of water is unusually high. It takes a whole calorie to raise 1 gram. I should add that in there later. 1 gram. 1 gram of water. Write that down. 1 gram of water, 1 degree Celsius. Right, that's a definition you might want to know. The specific heat of water. How many calories does it take to raise 1 gram of water 1 degree Celsius? Now it's very similar to the heat capacity, which is how much heat energy has to be absorbed to change a substance temperature. And again, with water, it's unusually high. This is good because, for example, we're living creatures, we're mostly water. It takes a lot of energy to change the temperature of water. So when we go outside and it's 117 out there, we don't start to evaporate, all right? Well, there's other reasons besides the heat capacity of water, but that's one of the reasons, right? And if we go into a climate that's snowy, we don't freeze solid either. Again, there's other reasons besides the heat capacity of water, but heat capacity protects water from wild swings in temperature. All right, so yeah, that's just what I said. And so this stuff's important. Might sound a little dry right now, but it's important and we'll use it later. Okay, phases of water. The phases, that's another thing. Water is the only substance on this planet that exists in all 3 of its phases, and the phases, of course, are gas, liquid, and solid. But it's the only substance on our planet that exists in all 3 phases, like in this picture, at normal surface temperatures. So, and in this picture, we've got, clouds, right? So we got gaseous water. You can see a waterfall, a liquid water coming down on the right, and at the bottom, this valley has a glacier in it. So solid water, the only one. Okay, these are our 3 phases. The question is, which do you think would be the most dense phase? And don't forget what density means, mass divided by volume. Which one of the phases do you think would be essentially the heaviest? Well, we know it's not going to be the gas, right? Would it be the solid or the liquid? Too bad I can't find out what you think. For water, the answer is the liquid. That's why ice floats on water. For, I think, every other substance on this planet, the answer is the solid phase. So this is a picture, I think, from the Lord of the Rings, right? When the ring finally goes back into Mount Doom and it's going to be melted in the lava and go back into the lava, right? So what happens when the ring is on the surface, it doesn't float there. If you have molten metal and you make it into solid metal, it is denser, it condenses and it's denser. And so the metal ring would sink down into it. It won't float there for long. It floats there dramatically in the movie for a couple seconds, but then it sinks. Okay, so anyway, this is also unique, and it's also important to life on this planet. If it didn't work this way, the oceans would freeze from the bottom up, and because the solid ice would sink, because it would be heavier than liquid water, and it would probably cause the planet's oceans to freeze, and that would be bad for life. We need liquid water on this planet. Okay, how heavy is water, right? How dense is water? I don't think I'll put this particular number out there. Well, it's 1 gram per centimeter cubed. It's really actually easy to remember. The only thing that would be hard to remember would be at 39 degrees Fahrenheit, kind of cool temperature. What that should tell you, Well, one thing dense that is rather dense for a liquid. I mean, it's not the densest liquid on this planet, but it's pretty dense. But the fact that the temperature is there should tell you that the density of water is dependent on temperature. Now, this is a rather complicated looking thing. I'll try and walk us through this. And there's another figure similar to this in your book, 610 on page 175. It's more complicated because this here is just, this is fresh water. And the figure in your book actually tells you the densities of seawater and at different salinities too, so it's more complicated. But let's just go through this, all right? On the left-hand side here, on the y-axis, we have density in grams per centimeter cube, density. So basically, how heavy is it, all right? And we're just talking about fresh water here, okay? So we know now that fresh water has different density. We know it's 1 gram per centimeter cubed at 39 degrees Fahrenheit. Do we have that on here? No, we have it in Celsius. So it'd be about here, see, 39.16. Okay, so it's right about B. Now, the x-axis is the temperature. So this tells us immediately the fact that we've got a graph where density is dependent on temperature, that the density of water changes. This line up here, this is supposed to be the density of fresh water depending on the temperature. Low, very low temperature, high temperature. Very low density, very light. Well, it doesn't change much. It goes from 0.917 grams per centimeter cube to 1 gram per centimeter cube. So it's very tiny difference, but that tiny difference makes a difference between whether water can be used to create life or not. Okay, so it does matter. All right, so what else do we have? So let's take an example. A there. It says density at 20 degrees Celsius, so right above the 20 degrees Celsius, right? That's pretty warm, right? That's, what is that like? 68 degrees. Is 0.9981 grams per centimeter cubed. Notice it's kind of low, like right about here. This is the lowest, that's the least dense, the lightest that water can be. This is the most dense, 1, all right? So that was at 20 degrees, it's about 0.9981. So it's not as dense as it can be, but it's a lot denser than D and E. Now, that's what we were talking about in the last slide, right? The maximum density of water is 1 gram per centimeter cubed at approximately 39 degrees Fahrenheit. Now, what happens when it gets colder? Okay, so this is when it turns to ice. When it turns to ice, it becomes less dense, and that's why it floats on the liquid water. It's lighter, it's 0.917, and actually gets a little denser once it gets colder than that. And let's see here if there's anything else I wanted to show you. No, I guess I'm going to skip that. But you see, we have 0 degrees here at 32, and it's got a density of 0.999. And then when it actually freezes, it changes and becomes less dense. I hope I have a picture of it changing. All right. So let's see. I ask here, what is the density of water at 0 degrees Celsius just before it becomes ice? Well, we just looked at that. The reason I ask you a question like that is kind of a clue that I might put a question like that on a test, meaning I expect you to understand these graphs. Don't just sit there and say, well, I don't really get this. If you don't really get it, watch the video again or look in the book, you know, and read it slower at your own pace. Because I might give you a graph like this and say, tell me something about this graph, and I ask you a specific question. Okay, so this is why. This is why ice floats, because this is a structure of an ice molecule. So what happens is, instead of them just roly-poling around like they were with their little mouse ears in the earlier picture, they suddenly pop open and they have this neat structure. Okay, and that structure, as you see, has holes in it, so it becomes less dense, and that's why ice floats. Okay, latent heat of fusion and vaporization. This is very college level stuff, okay? It's in the book. I'm going to go through it. If you don't get it the first time, read about it, okay? You know, if I'm going too fast, or if you don't understand, or feel free to let me know. But there's definitely going to be questions on the test about this. All right, so let's just start with some definitions. What is latent heat? Similar to heat capacity, except that we're not changing the temperature. So basically, latent heat says how much heat, you know, energy can be absorbed by a substance without changing the temperature. Without changing the temperature. We know that water has a high heat capacity. It takes a lot of heat to make it change. But now we're talking about latent heat. How much can it absorb without changing temperature? So latent heat of fusion and vaporization. So let's give some definitions of those. Vaporization is pretty close to evaporation. It's when water goes from liquid stage to gas stage. And there's going to be a time in there where it's absorbing heat, but it isn't changing temperature before it becomes a gas. Same with fusion, which we would call freezing. In this case, though, it would be, let me think, it would have to absorb heat to go from ice to a liquid. So I shouldn't say freezing, I should say melting. So if you're taking notes, I will change that. I will change that for the PDF. Okay. All right, so now this is in your book, and I'm going to explain it as best I can. Again, feel free to ask me questions, right? So I always start, when we have an XY graph, look at the X and the Y. Okay, we got temperature on the left side. Okay, temperature. And down here we got heat in calories per gram. So we're finding out how temperature changes with response to putting in heat, putting in calories. All right, we'll start with ice. Okay, ice. What about ice? Okay, ice is this little section here. All right, do we have temperature? Yes, minus 40 degrees to 0 degrees. That's where Celsius. That's where ice is created, okay? So we know that all this part is ice. Now we look at this part here. We can have liquid water from 0 degrees to approximately 100 degrees Celsius. So this whole section is when it's liquid. And then last but not least, we know water boils and becomes vapor once it gets past 100 degrees. Okay, so this section represents the vapor stage. Now, the latent heat of fusion means how much energy does it have to absorb to go from liquid, no, wait, sorry. Liquid heat of fusion. Do you take, so you gotta, if it's easier when you understand these things than when you memorize them. I have to try, I understand things, and sometimes I don't have things memorized, so you have to watch me think through it again. The latent heat of fusion, that means the amount of heat it takes to make something solid, but that would be the opposite, because solids don't move around. See, this is how you should think about it. Solids don't move around as much as liquids do, right? So they have less energy. And gas, for example, has lots of energy because it's moving around a lot. So you're actually going to take energy away if you're going from liquid to solid. So what we're doing, the latent heat of fusion, is actually the amount of energy it takes to go from solid, because you got to add the energy, to liquid. So to break those bonds, that is keeping it in a rigid shape and make it into a liquid. So what is that? What is that heat of fusion? How much energy does it take to break the ice bonds and make it into a liquid? Well, we can look down here. The heat, the heat is the calories. And we go from approximately a little less than 20 calories here. Oops, didn't mean to hit that. 20 calories here to 100 calories. So if I asked you on a test and I gave you this thing, what is the latent heat of fusion? You'd say, well, fusion is, well, fusion is making it into ice, but I really think they have that kind of backwards. And they even tell you the answer. It's 80 calories, right? But you can figure it out because you can see that, okay, it goes from liquid to solid right here on this line, and it goes from 20 calories to 100 calories. So that means you need 80 calories. Now notice, because we talked about before, what was our definition? What was the word? I have to look it up. Sometimes I don't have all my words at the top of my head. Latent heat, yes, that's what I meant. Latent heat. So how much, this is latent heat. Why? Because this 80 calories is being added to the ice and it's not changing the temperature. See, because it's a flat line there. It's staying 0. You got ice right here at D. You add 80 calories and now it becomes a liquid at C, but the temperature did not change. So that's latent. Okay, so again, I might be going a bit fast. There's a lot to comprehend here. Feel free to look at it at your own pace in the book. This might just help you sort of get the idea. All right, let's do the last thing with the latent heat of vaporization. This one makes more sense because we know that it takes more energy to be a gas than it to be a liquid. All right, so we know we got to add calories to our liquid to make it jump out of the pan. We're boiling it, okay, and jump into the atmosphere. It takes a lot of calories. They tell you how many. 540 calories for every gram of water to make it go from liquid to gas. So if you've ever wondered why it takes water so long to boil, that's why. It's got a high latent heat of vaporization. And you could figure out the 540 if I didn't tell you, and I just gave you this thing on the test. You could see that, look, water vapor here is at, what is it, like 700, it looks like it's like 740 calories it takes. And then over here, the F is 200 calories. So we subtract those two and we get 540. So you added 540 calories, and it's latent heat because it doesn't change the temperature. So while you're boiling the water's staying at 100 degrees. The vapor, this water vapor that's coming off the top, now that might be hotter, but the water itself is just adding those calories until it gets enough energy to leave. And this is why steam burns can hurt you really badly. Like if you've ever been in a sauna or if you've ever gotten a steam burn from cooking or something like that, because it works in the opposite way too. So you get that water vapor and it comes onto your skin, and it hits your skin and it condenses, so it goes from being water vapor at 740 calories down to liquid water that appears on your skin. It loses 540 calories per gram of heat. So it burns you. That's what burns you, is that heat being given off while it changes from a gas down to a liquid. This is also why jumping in a pool and getting out cools you off really well, right? When you're really hot. Because all that water that's on your body, as it evaporates when you get out of the pool, is taking 540 calories per gram with it. And of course, that's why Mother Nature has let us sweat, because sweating is our best way to get rid of extra heat, because every time we sweat and it evaporates, it takes 540 calories per gram with it. Which is why it feels hotter when it's more humid, because when it's dry, it can evaporate and take those calories away. When it's humid, you can't. You sweat and it doesn't evaporate. So you're just miserable, right? Isn't it neat to understand how things work? I think it's just cool. All right, so yes, this is added or subtracted depending on whether you're going from liquid to gas or gas to liquid. If you're going from ice to liquid or liquid to ice. And again, if you can just remember that when it's solid, it's not moving around much, so it doesn't have as much energy. So it has to have more energy. You'd have to add energy to the ice to get it to be liquid, where it can move around more, right? And that doesn't move around as much as the gas, so you have to add energy to the liquid to make it a gas. and then it goes the other way when you go down. So you subtract. You say, to make it a gas, if I got to make it turn into a liquid, it's going to have to get rid of some of that energy. Settle down a bit, boys. And so it's subtracted. And now you've got this liquid, and you say, okay, chill out. I'm going to make you into ice cubes. You're going to have to get rid of some of that energy. So you take it away. Okay, so these are questions to ask yourself and see if you can answer them. Again, good way to get ready for tests, right? If you can explain this, because this is kind of what I just told you. In fact, I would pause the video and see if you could answer that, because you want to do it while it's fresh. And if it's not, you still don't understand it, hopefully you have the book. You can look it up, or you can just Google it. Okay, there's a couple questions like that. Okay, because there will be questions about this on the test. I want you guys to be smart. All right, that's it for now. We'll take a little break and do the next part.